So I'll start. Heavenly Father, we thank you for this day again. Lord, I thank you for the students and for your creation, and that we can understand so much of it, Lord. In your name I pray. Amen. Okay, so yeah, we really do live in a kind of exciting time. So many things in nature we have some sort of, mathematical description of, much more so than, not too long ago. Let's see here. So what I wanted to talk about today is essentially gauge theory from a physics perspective somewhat. And although, in fairness to physics, there is a notion of gauge theory in physics which is a lot more general than what I'm showing today. For example, if you look at the book by Hanot and Teitelbaum, there's a well-developed theory of phase space, and it's just there's many theoretical things that are interesting and more general than what I'm about to show you. So what I want to do is try to start with, let's see here. Start somewhere small. So I probably should start with the F mu nu. F mu nu, partial mu A nu minus partial nu A mu. This is the so-called field strength tensor. I mean, if you remember advanced calculus, you might remember this as these are really the components, the components of a two form, right? So you can see that I'm trying to find something in here, and it's sometimes it's too fancy for me. I'm foolishly attempting to find bits and pieces from this book. It's Anomalies in Quantum Field Theory by Reinhold Bertelsmann. This is a well-known reference. Many people, at least when I was in grad school, who were working on becoming string theorists, rite of passage working through this book. And but it's pretty clear usually, and so I think I can find what I need in here. And that's what I'm trying to do, because my memory on what constants to put in front of things and things like that's a little rusty. So getting to it here. Stink. Sorry, give me a second. I'll find it eventually. Well, I mean, the A here is so A0 is like the voltage, and A1, A2, and A3 would form the vector potential. But there might be a factor of C depending on our our conventions. All right, let's see if I can get it. Okay, so the Lagrangian for this is something like -1/4 the conventions in this book, at least. Oh, come on, sorry guys. I want the one with current, I gotta find the one with current. Where's the one with current? Oh, there it is. So -1/4 F mu nu, F upper mu nu, all right, plus J mu A mu. No. I mean, it doesn't matter. J upper mu. So there's some conventions I'm using here, right? So I'm using the Einstein summation notation. So if the index is both up and down, that means that there's an implicit summation there. To be more explicit, this could be rewritten minus 1/4 G upper mu nu F mu nu. Oh, I'm sorry. Too lazy. We need one copy. G mu alpha, G nu beta, F F mu nu, F alpha beta, like that. Right? So you could rewrite it like that. And let's see here. So what are the Euler-Lagrange equations? So the action here is something along the lines of we integrate this Lagrangian, something like the integral of the Lagrangian over four-dimensional space-time. That's the action. Something like that. Well, actually, I think it's that. Sorry, this book has a lot of things on higher physics that I'm trying to ignore about field path integrals. And you guys seen moment generating functions in your statistics 311 or 411 class? 401? Oh. There's something called moment generating functions in statistics that are very, very cool. Well, let's see. How can I describe? Well, that is a digression I must avoid. But basically, there's just something called a Feynman introduced this generating. Is it generating functional? Oh man, I'm rusty. Anyway, it's this very neat, tricky integral thing that you can, through pretty systematic derivatives, generate terms that correspond to Feynman expansions, and so it's a very slick way of answering certain combinatorial questions that, through traditional means, are much more complicated. If you look at a book like, well, the standard book when I was in school was Peskin and Schroeder. But anyway, so this is the action, something like this, and so basically the equations of physics become that the variation of the action is 0. All right. And so here, this action is a function. I mean, so I guess we can either, well, you notice really, oh, and I lost my J mu A mu, right? So can we rewrite this thing just in terms of, so there's a helpful notation. Well, I'm not sure how helpful it is at the moment. Made myself a problem here. All right, so this is minus 1/4. I'll get to the point here eventually, guys. Minus 1/4 G mu alpha G nu beta, and that is, I'm going to use abbreviated notation. Partial mu A nu, partial alpha bracket alpha A beta close bracket. So this notation, let me make it red. What this notation means, guys, is antisymmetrize on these indices. So this is kind of a really cool, slick notation. This is, in my current notation, and you got to be careful because some people throw in factors of a half into this. I'm not doing that. I'm just taking it as it stands. This is the definition. All right. So it's called antisymmetrizing the mu and nu indices. So with this notation, you could say stuff like this, right? E1 wedge E2 is E1, well, you could say something like this. It's E1 tensor E2, like that. Antisymmetrizing in 1 and 2. But anyway. Okay, so then, of course, still plus the... Now, over here, guys, here's interpretation. The J mu... All right, so... So, let's see here. J mu is up to plus or minus here. The first component is the charge density, and this, the last three components is the current density. So this is dq dv, right? And this is current density. That's the current per unit area time. And charge flowing through a particular area per time, current density. So the current density and the charge density together give you what's called the forecurrent, J mu. And like I was saying, the interpretation of that is something like A mu. Again, up to, I'm not sure, plus or minus the first component. I can't remember plus or minus the thing. But the potential energy, the voltage, I'll use V for voltage. And then over here, the so-called vector potential. Maybe I should use something else. I don't know. Phi, the voltage, potential energy per unit charge. Okay, so with respect to the electric field. All right, so this is the Lagrangian expressed in terms of the one form, the A's. A sub alphas. And then, so what the Euler-Lagrange, you guys remember Euler-Lagrange equations? So we talked about Euler-Lagrange equations in advanced calculus. We said we, vary the action that gives us the Euler-Lagrange equations. These equations, the A sub mu, these are functions of space and time. So it's a multivariate Euler-Lagrange, and so what that looks like is the following: partial x upper mu of partial L partial A lower mu is equal to partial L partial of partial curses. Come on. Sadness. Grief. I can't remember anything, you guys. Come on. Phi is the voltage, and A is the magnetic potential. So the curl of A vector gives you the magnetic field. Dang it. I have the wrong book is what I have. I need a copy of Rider. Stink. So again, the action is the integral over appropriate region of space-time, I suppose, of the Lagrangian, which is actually the Lagrangian density here. And so the variation of S being 0 should imply the Lagrange equations by much the same. And let's see here. So I should be able to. Over here, I'm sorry, I need to cheat for a second here. So the usual Lagrange equations are ddt of something like partial L partial x dot, right? Equals to partial L partial x. So it's just that, but instead of having just time, you now have, 4 independent variables: x0, x1, x2, x3. And so instead of having x dot here, so this, I've got it. The thing I'm confused about is I was putting here what I should have put. So this is supposed to be partial mu here it is, A nu. And then over here, we're looking at partial L, partial X, I believe. No. x nu, I think. Yeah. I'm a little bit uncertain about my placement of indices at the moment. It's got to be something like this. So there's a sum over the mu here, but there's a free nu on both sides. Or something like this. So what's partial L, partial? I think I'm doing right. Partial. Sorry, I didn't know the words for it. Partial L, partial nu, a nu. Can you? So we should have something like partial x mu of what? You look at this, right? And really, we should use something. We should use some letters other than mu and nu. So the mu and the nu and the alpha and the beta are summed over up here. So we're going to get into trouble if we use the same letter. We should use different symbols down here, like say kappa. And what have I not used yet? Tau. This seems, I should have left the, anyway. I feel obligated to put the tau downstairs over here, but I'm going to put it there. Anyway, so that's probably not quite right, but you'll bear with me. So sorry. So partial x kappa. Can you, so try to, what's this partial derivative here? If you look at it, this picks up one term. So I got like a minus 1/4 g mu alpha, g nu beta. And what do I get? I get, you know, Kronecker delta, kappa mu, Kronecker delta, tau nu, minus Kronecker delta, kappa nu, Kronecker delta, tau mu. And that's all times partial alpha beta, right? But if you look at it, let me just not go through the full calculation here. Basically, you get the same thing again with the other term, but because of the symmetry of the contraction and the fact that these are the metric tensors symmetric, long story short, what ends up happening is that this becomes a half, if I remember right. And then, of course, this term has no, this is 0. J mu a nu, when you differentiate it with respect to that, it's 0. And then on the other hand, what's partial L partial? And that should not be x tau there, should it? Certainly not. Certainly not. What should be there? Partial L partial what? Ah, it's fine. If you want the water bottle.
Oh, that's not mine. But
It's been sitting there. I mean.
thank you.
Okay. Nothing else. I think this place is slowly but surely turning into lost and found for this building. But anyway, so I'm. It should be tau. The thing that I'm really burying the lead here. So what is the solution to the ordinary Euler-Lagrange problem that we talked about in advanced calculus? We're thinking about paths that solve some action functional, right? So we're talking about like path of least time or something like that. But the solution is a function, a parameterized function of time. in 1, 2, or 3 variables typically. That was the variational problem we looked at in advanced calculus. This is a very different problem. Here, the variable is a field. We're looking for a function of space-time, a sub tau. That's the solution. We're varying over possible functions, a sub whatever. So it's that's what we're after. We're trying to vary through the space of these a's and find the choice a which maximizes or minimizes the action. Right? That's where the Lagrange equations are coming from. And so this here is just equal to what? J mu, right? Kronecker delta mu tau, also known as J tau. And this right here, well, that's F. This is F alpha beta. Right? And when you sort through this mess, what you've got is, let's see here, partial x. I mean, I'm kind of worried to sort through it because I might have enough things wrong that we can't make sense of it. So sorry. But if we use these Kronecker deltas in here, what happens? We keep the what? We keep the kappa. The mu becomes kappa, right? Mu becomes kappa. So we get G what? Kappa alpha, right? And then what's the other one? G nu becomes tau beta. Okay, and then plus 1/2. And then I'm doing the other Kronecker delta. So now the nu becomes kappa, right? And I'm sorry, I can't keep things straight here. So what you guys read it for me? Mu. So tau alpha, right? G kappa beta. And that's all being, we've got this F alpha beta over here, right? So we're taking the derivative of this mess, and it's all going to be equal to J tau. All right? If I had more sense, I wouldn't even be going through this, but once I start it, it's like a moth to a flame, So what happens here? This raises the indices to what? So we take this alpha beta index, raise it to F, looks like kappa tau, right? And then this plus, there's a minus here, right? F what? Yeah, tau kappa. But this is antisymmetric, so what you have is partial F tau kappa, partial X kappa equals J tau. This is hideous. Let me rewrite that properly. This is partial mu of F nu mu equals to J nu. not 100% certain about the sign on this. But anyway, this is the right thing. And that's why there's a fourth in the definition. The reason for the minus 1/4 here is precisely because of this, because those are Maxwell's equations. Now we looked at this in, I mean, what we're looking at is the component. I think we're looking at the component part. Well, I have a slight worry, but anyway, this is Maxwell's equations with the current. I mean, there's another set of Maxwell's equations, right? If you just calculate, you know, partial mu of. See, this is weird. How can that? Huh. I mean, the other Maxwell's equations is what? It's. I'm bothered here because I remember something about the dual tensor entering in here, and so this is troublesome to me. Oh. Wow. Huh. Well, there are much nicer equations in this book. For the record, I'm talking about page 158. But anyway. All right, so I'm sorry, Well, anyway, there's a pure gauge part to the Lagrangian, and then there's a source part, right? So the pure gauge part is the f with f, and then this is the source term, right? With the j, that's from an external current and so forth. Okay, the thing that's bothering me, guys, is that I mean, we have the one form potential A, remember? It's like something like minus phi dt plus the work form of the vector potential, and then we calculate d, or maybe I just use A for it, right? And then we calculate dA, we get what? We get minus d phi wedge dt plus the curl of A, and then how's it go? Trying to remember how to write the other. Here, A could be a function of time, so the exterior differentiation also involves a time derivative. It's like a homework problem for you guys. So I got A1 dx, A2 dy, A3 dz there. I take the differential with respect to time. How to write that? I think it's just plus dt wedge the work form of partial A, partial t. Yeah. And so that gives us the Faraday 2 form, right? This gives us F, which is also if I recall correctly, it's the work form of the electric field, wedge dt, plus the flux form of the magnetic field, right? Up to a sign. So, I mean, A is the sum over mu of A mu dx mu, right? So dA is the sum over mu and nu of partial nu A mu dx nu wedge dx mu. all of a sudden I'm summing over mu because I'm back in my math land. Sorry. It's somewhat uneven. Yeah. And so that's why I was rattling off to you guys at the start that that's the Faraday 2 form, you know. So when we write F mu nu is this antisymmetric difference of partial derivatives of the A, that's the field strength, which includes both the electric and magnetic fields in it. Yeah. Seems like I did I feel like the Hodge dual or something came in as it relates to the current density, though. Like it was something like man, I just can't remember anything today. Just a second. I guess I should just look up Maxwell's equations, yeah. (287 to 290). All right, there's hope. This is where I should have been looking. Idiot. Yeah, so here he eventually tells us that df equals to 0. I mean, that comes from d squared a being 0, right? So that's what's worrying me is when I was thinking about what does that mean at the level of partial mu a notation, right? What does that look like? Anyway, focus here. And then there's the Hodge dual of F. Oh, here it is. Oh, he writes them finally. So he's got partial mu of the dual of F mu nu equal to 0, the homogeneous, and partial mu F mu nu equal to J upper nu. That feels more right to me. There's a sign error in what we worked out just now. Like this feels right, that this index matches that like that, not, see, I got twisted here and somewhere in there. I'm not sure where. So sorry, guys. So the homogeneous, though, it's not just involves the dual there, yeah? And if you're wondering, here's the dual mu nu. It's 1/2 epsilon mu nu alpha beta F upper alpha beta, sum over alpha and beta implied. And that's the antisymmetric symbol. So that's the meaning of that star. And then still star dual F upper mu nu is something yet different than what I have written on the board. You still need to take this thing and raise the indices up. And then that thing is what gets the homogeneous Maxwell's equations, which we know and love as divergence of the magnetic field is 0 and the curl of the electric field is minus partial B partial T. So both of those Maxwell's equations are implicit within this, and Gauss's law and Ampere's law with Maxwell's correction are in here. All right. So, what is the gauge transformation then is the real question I want to get at. I'll eventually get back to it. Too many sticky notes. They're leading me astray. So I'm not sure that the gauge transformation's all that interesting in our current context. Let's see here. Does he at least write it down somewhere? I'm nervous to write it down. Well, I mean, you can see the gauge freedom in part where that if we add, you know, F is equal to dA, right? But it's also equal to d of A plus the differential of whatever, right? So the A is not uniquely fixed as it's related to the, the field strength, the F. Different choices of A will still yield the same physics. And then the question is, how are you allowed to vary A, maintaining the equations, Maxwell's equations that I boxed there? But so I think, in short, we can add the differential of a function here. Now let me turn the page here and try to at least write down the formulas for what's called Yang-Mills theory. All right. So this is section 3.5, which is the Fadeev Popov method for non-abelian gauge fields, and he says so. This is from 1954, Yang and Mills. He starts with a free fermion theory. Okay, so I'll follow his notation. L sub upper 0, lower psi, equal to psi bar. I partial with a bar through it, minus m, acting on psi. Okay, so you might wonder what that means. You guys know what? Do you know what this means? Have you ever seen that notation before? Standard what? Standard model equation? So it's in stuff you've read on the standard model? Yes, that is correct. I thought that he had a page of notation in here somewhere. I think I know what that is, but I'm a little rusty. I'm pretty sure it's well, I better not. I know it involves h bar, where h is Planck's constant. All right, come on. I swear. Yes. It is related to Schrodinger's equation. Come on. I can't find anything today. Oh, wait. When you know something, you don't even think about knowing it. But once you don't know it, it really is annoying. Oh, well, finally. I found something else. Here's the abelian gauge transformation. A mu transforms to a mu of x, transforms to a mu of x. plus partial mu lambda. In other words, you can add a derivative to it. So gets the gauge transformations for what we're that's what gauge transformations for the potential look like for electromagnetism. Okay. So we found that. Yay. Come on. This is just standard notation, guys. I just can't remember it. It might not even be in this book. It's so ubiquitous in physics that it is a shame that I don't remember it. It's very much bothersome to me at the moment. Yeah, if you search Dirac's slash notation while I'm suffering. Yeah, no, I think you're right. I mean it's a universal notation like for example, maybe you've seen h bar. That's h over 2 pi, I think. Is that it? Is that right? Or did I just remember that wrong too? So what's that partial mean there? See, I am really annoyed that I didn't take 5 minutes to find a copy of Ryder's quantum field theory before I talked to you guys today, because it would have helped us a lot. All right, I have to stop with this. Let me just chill. This has a specific meaning. And so these are spinors, all right? So these are fermion fields, which means that if you calculate the Euler-Lagrange equation for this piece, you get, you get the Schrödinger equation, I believe, for that fermion field. Now, okay, so in addition, he says, we assume that the fermions still have internal degree of freedom represented by a vector in some group space G. So, for example, psi also has some quote-unquote internal degree of freedom. For example, we could have psi is equal to Q, he says QP, QY, QB, which is pink, yellow, and blue. This would be a SU3 representation. And Q denotes a spinor field for a certain flavor of kind of quark. Q could be up, down, strange, charge, bottom, or top. Great. Gauge group. Gauge group G of X in G, all right, transforms the spinor fields via the following rule. Psi G of X is equal to G inverse of X times psi of X. And the conjugate field, well, guess what? Psi conjugate of X times G of X. With G of X equal to e to the lambda x, big lambda x, and lambda of x is actually equal to itself lambda a of x TA. Now here, this is a sum over like an SU3 index. That's a sum over the internal degree of freedom. That's not like a mu or a nu. It's not a space-time index. That's over the gauge group. And the matrices TA are generators of the group, and they satisfy the algebra relation. TA TB equal to F ABC TC. In other words, these are the structure constants of the gauge group FABC. In particular, if we have FABC equal to 0, that returns us to the abelian case, which we already looked at in the other two boards. He says here the matrices are chosen to be anti-Hermitian, and they're normalized such that the trace is minus 1/2 delta. And then he says some things about how you can construct the T's either for SU2 or for SU3 in terms of either the Pauli matrices or the Gelman matrices. They're explicitly given here on page 160. And let's see here. I'm trying to get to the point. So he tells us things about Lie algebras at this point. Okay, so now let us return to the Lagrangian. So the thing is with this Lagrangian here, right? And you look at these gauge transformations, right? What happens when you transform the Lagrangian, the free piece, right? This is the so-called free Lagrangian for the spinor field, okay? This is just the I mean, in the absence of any gauge symmetry, this would be the Lagrangian, and then the variation of this Lagrangian would give us the equations of the field equations for the spinor psi. So what happens to this Lagrangian if we think about varying it? If we think about looking at a gauge transformation, what happens to the psi and the psi bar? If you just look at the M piece, see what happens with psi bar? Psi bar goes to, like, if I look at, my question is, what happens with psi bar G, I partial bar minus M psi G? Like, how does that work out if we do the gauge transformation of the spinor field? Again, it's a local gauge transformation because the gauge, you're multiplying the fields by a SU3, a different SU3 element at different points in space-time. Well, you see what happens, right? If you look at the psi bar G, you get a psi bar GX, right? And over here from the psi G, you get a G inverse psi X. So the G and the G inverse, poof. And this piece is just straight up gauge invariant. But this is a derivative term, which I have not been able to explicitly describe for you guys. But it differentiates. And of course, when you differentiate psi G, you have derivatives of the space-time varying gauge parameter. And so there's a product rule, right? Now, part of that product, I think, is still going to, behave well. Anyway, so that then forces us to add another term to the Lagrangian to compensate for that in order to maintain the gauge invariance. So this is what you do. Your new L naught. He calls this L naught. Oh, I can't write here. What am I doing? All right, so getting to it here. So let's see here. We have. I'll just write it down. Maybe we can understand it together. L naught psi G. I think he's just saying what. I think he's just at the moment he's just saying what this transforms to under that gauge transformation, which I was just describing. But here it is. It's psi bar I partial slash minus m psi plus I psi bar g partial slash g inverse close parentheses psi. Okay, yeah, this is the result of what I was just talking through. When you actually just transform this to psi g, right? You have the piece which is with the g and the g inverse canceling, right? So this part is from g inverse, equal to 1, and this is left over from the product rules, which result, right? You guys understand what I'm saying? You notice that the psi bar has what? Psi bar has psi bar g. See that? Psi bar g. And then partial bar acting on g inverse. The partial bar acting on psi, it's over here. I'm missing, oops. That's over here, and of course the g's are already canceled out. All right? Great. So he says, analogous to the abelian case of QED, we introduce a gauge potential. Introduce a mu of x equal to a mu a of x ta. By the way, I should really have gone through this. Maybe I'll go through with you next time. I don't know. Maybe it's worthwhile, maybe it's not. In the past, I've gone through it with you guys. Or not, maybe not. I might have done this in your advanced even. But if we look at a complex scalar field theory over U1, not a spinor, but a complex, complex scalar field theory, it's something more like this. I forget exactly. Something like this, though. And then, so this is a scalar field theory. Phi is just complex valued. It's called a scalar field. Like the Higgs field, for example, is such a thing. And spin 0, whereas the psi is a spin 1/2 field. That has to do with how it couples to the magnetic field. But that actually motivates the introduction of the A sub mu that we've talked about for electromagnetism through a similar argument to the one we're going through right now. So what he's going to say is that if we introduce this A and add a term to the Lagrangian, we're going to be able to nullify this piece and maintain gauge invariance under the transformation by introducing this new gauge potential field. Something I should have been saying all along today, so sorry. Gauge potential field. That is the gauge potential. Why have I not said that yet? Said. Anyway, so here's the really weird thing. How does the gauge potential transform under a gauge transformation? A sub mu upper G. And this is weird, guys. Check this out. G inverse A sub mu G plus G inverse partial mu G. This is one of the things that Yang and Mills invented for their Yang-Mills theory. They said there has to be this thing, the gauge potential, and it has to transform like that. In the abelian case, a lot of this wasn't present because G and G inverse, they commute with everything. I mean, what does this simplify to in the case that, if it's an abelian group, this just simplifies to what? A mu G equal to A mu plus partial mu G. Well, times G inverse, I suppose. Right? Which can be rewritten like we did before as just the derivative of a function. So in the abelian case, this gauge transformation is not as well funky, really. And so in physics, they say this basically corresponds to, here's their slogan, replace derivatives with covariant derivatives. In particular, we trade partial mu for d, big D mu. Big D mu is partial mu plus a mu. This is also sometimes called minimal coupling, for reasons I don't really understand. And so, in this wild, so the Lagrangian then, in this new world of non-abelian gauge theory, the Lagrangian is as follows. The psi piece, you just you change it to psi bar I d slash, which is the same to d as partial slash is to partial. So whatever we don't understand, we've not increased the net amount of not understanding. So there's that. Sorry. Whatever convention it is that I've forgotten about the stupid partial slash. Oh! You know what I think, guys? I think partial slash is actually a notation for, I think it's actually gamma mu partial mu, where these are the Dirac matrices. It's actually somewhat involved. Because it's got to be something that involves derivatives of space and time, and it's got 4 things, and it's anyway, yeah. Anyway, this cool. This is part of the Lagrangian, but then what else is there? He says there's also a Yang-Mills piece. The pure gauge piece is -1/4 F mu nu upper A F upper A mu nu. In other words, with the conventions in this book, that's 1/2 the trace over the gauge group, over the SU3 matrices or whatever. So the Yang-Mills is actually the trace of the contraction of the field strengths. And here, in this context, F mu nu without an index is understood to be a sum of matrices against, well, functions of space-time. So F mu nu A, TA. And here's where it gets interesting, guys. F mu nu, well, this is now partial mu A nu minus partial nu A mu plus the plus the bracket of A mu A nu. That term we would not have seen before, because in the abelian case, when you take the take A mu A nu minus A nu A mu, and you're carrying at most like a complex scalar, it just cancels. But here, A mu and A nu, these are carrying matrix representations of SU3 or SU2 or something, and so that bracket doesn't have to vanish. And so if you do a gauge transformation of the field strength, it's equal to G inverse F mu nu. So this is how the field strength transforms. It transforms like G inverse Fg, like that. And that's actually, you got to understand, that's a significant calculation I'm suggesting right now. What I'm saying to you guys is that if you put this boxed relation into the definition of F over here, all right? So plugging this into that defines this, which works out to that. And that's why this is gauge invariant. See, because if you do a gauge transformation,